Lowe's knows when you're looking for reliability, the right brand makes all the difference. And now, Lowe's is the exclusive home improvement retailer for the Whirlpool water treatment line, including their Wi-Fi softener, under-sink filtration system, and more. With Whirlpool's proven performance and our everyday low prices, better tasting, better quality water is within reach. Shop pro-trusted brands like Whirlpool and more, in-store or online. Lowe's. We help, you save.
This is SpaceTime, Series 28, Episode 94, for broadcast on the 6th of August 2025. Coming up on SpaceTime, a new study says the Milky Way could have far more satellite galaxies than previously thought. NASA's Mars Curiosity rover reaches new heights on the red planet's Mount Sharp. And NASA releases the closest ever images of the Sun taken by the Parker Solar Probe. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Our Milky Way galaxy could have more satellite galaxies surrounding it than astronomers had previously predicted or been able to observe. Cosmologists used a new technique which combines high-resolution supercomputer simulations together with novel mathematical modelling in order to predict the existence of up to 100 more small dwarf galaxies orbiting around the Milky Way. Of course, the best-known galaxies which we see orbiting the Milky Way are the Large and Small Magellanic Clouds and the Sagittarius Dwarf Galaxy, which is currently in the process of crashing through the Milky Way. Right now, the nearest dwarf galaxy to the Milky Way is the Ursa Major 3 dwarf spheroidal galaxy. But if these new hypothesized galaxies are eventually observed using telescopes, then they could provide strong support for the so-called Lambda cold dark matter model, which astronomers currently use to explain the large-scale structure of the universe and how galaxies form. The model suggests that ordinary matter, the stuff stars, planets, houses, dogs, cats and people are made from, really only represents about 5% of the total mass energy budget of the universe. Cold dark matter, an invisible substance which we can't see, but which we know it exists because we can see its influence on regular matter, makes up a further 25% of the total mass energy budget of the cosmos. And the remaining 70% is the even more mysterious dark energy, a force which we know exists because we can see it's causing the accelerated expansion of the universe and will ultimately determine the universe's fate. Now, according to the Lambda cold dark matter model, galaxies form at the centres of gigantic clumps of dark matter known as halos. Most galaxies in the universe are low-mass dwarf galaxies, the majority of which are satellites orbiting around more massive galaxies like Andromeda and our own Milky Way. The existence of these enigmatic objects has long posed challenges to the Lambda cold dark matter model. Many more Milky Way companion galaxies should exist than what cosmological simulations have so far produced, or what astronomers have so far been able to see. The new research shows that the Milky Way's missing satellites are extremely faint galaxies stripped almost entirely of their parent dark matter halos by the gravity of the Milky Way's own dark matter halo. These so-called orphan galaxies are lost in the simulations, but they should have survived in the real universe. Using their new technique, astronomers were able to track the abundance, distribution and properties of these Milky Way orphan galaxies, showing that many more Milky Way satellites should exist and be observable today. The authors hope that new advances in telescopes and instruments, such as the Vera Rubin Observatory, will give astronomers the ability to detect these very faint objects, bringing them into our view for the first time. The study's lead author, Isabel Santos from Durham University, says astronomers know the Milky Way has some 60 confirmed companion satellite galaxies, but there should be dozens more of these very faint galaxies orbiting around the Milky Way at very close distances. The concept of the Lambda cold dark matter model is the cornerstone of our understanding of the universe. It's led to the standard model of cosmology and is the most widely accepted model for describing the universe's evolution and structure on large scales. The so-called cosmic web, where galaxies, galaxy clusters and superclusters are spread along fine filaments surrounding huge voids of near-empty space. The model's already passed multiple tests, but it's recently been challenged by puzzling observational data on dwarf galaxies. The Durham University researchers say that even the best existing cosmological simulations, which include gas and star formation in addition to dark matter, don't have the resolution needed to study galaxies as faint as those astronomers are now starting to discover close to the Milky Way. These simulations also lack the precision required to follow the evolution of the small dark matter halos that host these dwarf galaxies as they orbit around the Milky Way. And this leads to the artificial disruption of some halos, leaving galaxies orphaned. The results showed that the halos of dark matter, which may host a satellite galaxy, have been orbiting around the central Milky Way halo for most of the age of the universe, leading to the stripping of their dark matter and stellar mass and rendering what's left extremely small and faint. As a result, the authors predict that the total number of satellite galaxies of any brightness likely to exist around the Milky Way is around 80 or potentially even up to 100 or more currently known. The authors are putting a special emphasis on the approximately 30 newly discovered tiny Milky Way satellite candidate galaxies that are extremely faint and small. But they say it's still unclear if these are dwarf galaxies embedded in the dark matter halo or they're globular clusters, collections of self-gravitating stars, which are either formed in stellar nurseries or the cores of small galaxies which have already merged with the Milky Way. This is SpaceTime. Still to come, NASA's Mars Curiosity rover reaches new heights on the red planet's Mount Sharp, and the Parker Solar Probe snaps its closest ever images of the Sun. All that and more still to come on SpaceTime. NASA's Mars Curiosity rover has reached new heights in its ongoing exploration of the intricate boxwork terrain on the slopes of Mount Sharp, the 5.5-kilometre high central peak in the red planet-scale crater. The 6-wheeled car-sized mobile laboratory has now arrived at the base of a steep ridge near a hollow, providing increasingly detailed views of these unique Martian formations. It's thought the terrain was formed by groundwater when it encountered crisscrossing low ridges, some just a few centimetres tall, and arranged in what geologists call a boxwork pattern. The bedrock below these ridges likely formed as groundwater trickling through the rock left behind minerals that accumulated in cracks and fissures, hardening and becoming cement-like. Then eons of sandblasting by Martian winds wore away the rocks but not the cement-like minerals, resulting in networks of resistant ridges that give the geology the boxwork name. The research marks a new phase in Curiosity's campaign to analyse the composition, structure and origins of the rigid terrain. To get there, Curiosity first needed to scale a steep 11-metre incline to reach the rim leading to the boxwork region. Here the rover deployed its MassCam and ChemCam instruments to capture mosaics of features, including the El Corral, Champar and Meson ridges. It then drove 15 metres closer to the Meson Ridge for a more detailed inspection. Other targets were also studied using ChemCam's laser to determine the composition and texture of the nodular bedrock. And it wasn't just the rocks. Curiosity also continued to undertake atmospheric observations, including a 360-degree dust devil survey. Initial observations using the NavCam and MassCam instruments quantified dust opacity, while a large MassCam mosaic detailed the ridge beneath the rover. ChemCam was used to focus on a vein of minerals named vicuna, while contact science instruments examined nodular bedrock targets Totoral and Silla, allowing scientists to compare ridgetop chemistry with the material in nearby lower areas. Scientists also examined more distant sedimentary boxwork structures and carried out atmospheric observations analysing the day and night chemistry and isotopic makeup of the Martian atmosphere. Later, NavCam assessed Gale Crater's dust opacity, while MassCam performed sunward dust measurements. Curiosity also examined a weird nodular rock called Lake Titicaca, using its laser spectrograph followed by a telescopic mosaic of sediment layers on the Mishimoqua Butte. This is SpaceTime. Still to come, NASA's Parker Solar Probe snaps its closest ever images of the Sun, and later in the science report, warnings that hailstorms could hit Australian cities harder and more often than ever before due to climate change. All that and more still to come on SpaceTime. On one of its recent record-breaking passes close to the Sun, NASA's Parker Solar Probe captured some stunning new images from within the solar atmosphere. The newly released observations were taken closer to the Sun than ever before, and they're helping scientists better understand the Sun's influence across the solar system, including space weather events which can affect life here on Earth. The images show the very region where space weather threats to Earth are thought to begin. The new data will help astronomers vastly improve their geomagnetic storm predictions. And that'll help ensure the safety of crew in space, as well as technology both on the Earth and throughout the solar system. Now, these specific images were taken during Parker Solar Probe's closest approach to the Sun back on December the 24th, as it skimmed through the corona, the Sun's outer atmosphere. In the days around perihelion, it collected data with an array of scientific instruments, including WISPR, the Wide-Field Imager for Solar Probe. The new WISPR images reveal the corona and solar wind, the constant stream of electrically charged particles which flow out from the Sun and spread right across the solar system. The solar wind expands as it travels through the solar system, and it results in some wide-ranging effects. Now, together with outbursts of material, plasma and magnetic currents from the Sun, it helps generate auroras, strips planetary atmospheres, and induces electric currents that can overwhelm power grids on Earth and affect communications and navigation systems. The WISPR images are giving scientists a closer look at what happens to the solar wind shortly after it's released from the corona. The images are showing an important boundary region known as the heliospheric current sheet. That's where the Sun's magnetic field direction switches from northwards to southwards. And for the first time in high resolution, it was able to capture the collision of multiple coronal mass ejection events. Coronal mass ejections are large explosions of charged particles, plasma and magnetic field, which are blown away from the Sun by solar flares, and they're a key driver of space weather events. In these new images, scientists are seeing coronal mass ejections actually piling up on top of one another. It's allowing scientists to figure out how they merge together, and that could be important for space weather studies. See, when coronal mass ejections collide, their trajectory can change, and that makes it harder to predict where they'll end up, whether they'll hit the Earth or whether they'll miss us. Their merger can also accelerate charged particles and mix magnetic fields, and that makes their effects potentially far more dangerous to astronauts and satellites in space, as well as technology on the ground. The solar wind was first theorized by heliophysicist Eugene Parker back in 1958. His theories about the solar wind, which were met with criticism at the time, have revolutionized science's understanding of the solar system. Prior to Parker Solar Probe's launch back in 2018, NASA and its international partners led missions like Mariner 2, Helios, Ulysses, Wind and ACE, which all helped scientists understand the origins of the solar wind, but from a distance. Parker Solar Probe, named in honour of the late scientist, is filling the gaps in our understanding much closer to the Sun. Now, usually at Earth distance, the solar wind is mostly a consistent breeze. But Parker Solar Probe has discovered that it's really anything but that at the Sun. When the spacecraft reached within 24 million kilometres of the Sun, it encountered zigzagging magnetic fields, a feature which scientists have now named switchbacks. Using Parker Solar Probe's data, scientists discovered that these switchbacks, which came in clumps, were far more common than expected. When Parker first crossed into the solar corona about 13 million kilometres from the Sun's surface back in 2021, it noticed the boundary of the corona was uneven and more complex than previously thought. And as it got even closer, Parker helped scientists pinpoint the origins of the switchbacks. It appears they come from patches on the Sun's visible surface, the photosphere, where magnetic funnels form. Last year, astronomers announced that what's known as the fast solar wind, one of two main classes of solar wind, is in part powered by these switchbacks, adding to a 50-year-old mystery. However, it would take a closer view to better understand the slow solar wind, which travels at just 360 kilometres per second, about half the speed of the fast solar wind. Parker Solar Probe project scientist Noor Rafi from the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, says the big unknown's always been how the solar wind is generated and how does it manage to escape the Sun's immense gravitational pull. Understanding this continuous flow of particles, especially the slow solar wind, is a major challenge for scientists, especially given the diversity of properties in these streams. The slow solar wind, which is twice as dense and more variable than the fast solar wind, is important because its interplay with the fast solar wind can create moderately strong solar storm conditions at Earth, sometimes even rivaling those of coronal mass ejections. Prior to Parker, distant observations suggested there are actually two varieties of slow solar wind, distinguished by the orientation or variability of their magnetic fields. One type of slow solar wind, called alphinic, has small-scale switchbacks. The other, called non-alphinic, doesn't show these variations. As it spiraled towards the Sun, Parker was able to confirm that there were indeed these two different types of slow solar wind. Its close-up views are also helping scientists differentiate the origins of the two types, which scientists believe are unique. The non-Alvinic wind may come off features known as helmet streamers, large loops connecting active regions of the Sun, where some particles can heat up sufficiently to escape. On the other hand, Alphinic winds may well be originating near coronal holes, dark, cool regions of the solar corona. In its current orbit around the Sun, which brings the spacecraft just 6.1 million kilometres from the Sun's surface, Parker will continue to gather additional data during its upcoming passes through the corona in order to help scientists better confirm the slow solar wind's origins. By the way, the next pass will be on September the 15th this year. This report from NASA TV.
Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe.
Ever since NASA's Parker Solar Probe launched into space in 2018, it has been circling closer and closer to the Sun and taking images along the way. In December 2024, it made its record-breaking closest approach to the Sun. That's when it took historic close-ups of the solar atmosphere, images that are changing the way we understand our star.
With images like these ones, we are actually going to have this full understanding of how the solar atmosphere works, and in particular, to try to predict the solar activity and mitigate its impacts.
The images were taken by the spacecraft's Wide Field Imager for Solar Probe, or WISPR, which observes space in visible light. WISPR doesn't look at the Sun directly. Instead, it captures solar material just as it comes off of the Sun. When it took these images, the spacecraft was only 3.8 million miles from the Sun's surface. If Earth and the Sun were 1 foot apart, Parker Solar Probe was about half an inch from the Sun. At that distance, the spacecraft was immersed in the solar atmosphere known as the corona. Here, streams of electrically charged particles flow outward from the Sun at over 1 million miles per hour, forming the solar wind that fills the entire solar system. These images reveal previously unseen details at the origin of the solar wind.
The amount of clarity and the amount of details that we got from Parker Solar Probe is totally unprecedented. But also we see phenomena that you didn't really see before, and that's where the fun begins. The most impactful events, multiple events that are one following the others, and understanding that interaction between CMEs will help us also have another view of their potency for space weather.
When the most impactful eruptions reach Earth, they can trigger auroras, but they can also harm satellites, disrupt power grids, and expose astronauts to dangerous radiation. Another key feature marks an important structure known as the heliospheric current sheet. The current sheet looks like a twirling skirt that extends out from the Sun and across the solar system. This invisible current sheet is a boundary separating where the solar wind's magnetic field changes direction from north to south.
It surrounds the whole Sun, and it never disappears. That's actually one of the regimes of the solar wind that we have to understand.
The current sheet is important to study because it can affect how impactful eruptions can be at Earth. We've never seen these phenomena in such detail before, and scientists are continuing to study these images to piece together how the Sun affects Earth and the rest of the solar system.
Parker Solar Probe is opening our eyes on a new reality about our star, the Sun. It is rewriting the textbooks for us.
This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study warns that hailstorms could hit Australian cities harder than ever before due to climate change. Findings by meteorologists at the University of New South Wales suggest that hailstorms will become more frequent, more damaging, and with hailstones increasing in size in Sydney, Canberra, Melbourne and Perth. For example, past simulations have produced large 10-centimetre hailstones once every 20 years around Melbourne, but a warmer future will increase that to once every 3 years. But the good news is modelling shows there'll be little change for people living in Adelaide. From smashed windscreens in Sydney to ruined crops across Queensland, hail is one of nature's most dramatic and often costly displays. In fact, hailstorms are responsible for more than 20% of insurance losses across Australia. The damage is largely driven by the size of hailstones, and the stones can get big. Australia's record, near Mackay in Queensland, is around 16 centimetres, more than double the diameter of a cricket or baseball. Hailstorms rely on warmth to start, so they usually occur during spring and summer when warm air is pushed up into cooler air higher in the atmosphere. Hailstone's size is controlled by how strong the updraft is in a thunderstorm. Inside these storms, these strong updraft winds carry moisture high up into the atmosphere where it freezes, forming ice particles. Now, these ice particles, initially known as hail embryos, pick up surrounding supercooled water as they circulate through the storm cloud. And the stronger the updraft, the longer a hailstone can stay in the storm and continue to grow. Of course, eventually, a hailstone gets too heavy to stay up there, and so it falls down to the ground. A new study has found that tube worms and rare mollusks, which live in the deepest parts of the ocean, are far more widespread than previously thought. The new findings, reported in the journal Nature, used a manned submarine to explore the deepest, darkest seafloor trenches in the northwestern Pacific Ocean. Scientists descended down into the blackness of the Hadell trenches at a depth ranging from 5,800 to 9,533 metres. The findings are shedding new light on the potential for life to exist in these extreme dark zone environments. See, the communities which occupy these depths have no access to light, and therefore they can't use photosynthesis to make energy. Instead, they use hydrogen sulfide and methane for chemical reactions in a process called chemosynthesis. The hydrogen sulfide and methane coming from deep-sea vents and black smokers found along mid-ocean ridges. A new study has shown that most research into computer vision technology, which interprets imagery, is actually focused on facial ID in detecting people. The warnings showing that Big Brother really is watching you are being reported in the journal Nature. The authors found that targeting people within this research field has become normalised, and that papers often used obscure language to hide the surveillance potential of their research by referring to people as objects. The study analysed papers from 1990 to 2020, along with patents which cited these papers. They found that the top two nations producing papers that resulted in surveillance-enabling patents were from the United States and China. The Australian government's social media censorship scheme is expanding to now include YouTube. Prime Minister Anthony Albanese claims the program is designed to protect children under 16 from bullying and access to inappropriate sexual content. Policing the scheme will require every Australian to obtain a digital proof of age ID. However, critics see it as the government's backdoor entry to enforce a Big Brother digital ID scheme on citizens who have already rejected the idea of an Australia card identification proposal. They point to examples like China's social credit scheme, which punishes its citizens who refuse to follow the government's directives. Then there's the Canadian government's decision to lock bank accounts of protesting truck drivers, and Australian police using the digital COVID vaccination passport to track people's movements. And it's not just social media and YouTube. The government's new legislation will also force you to establish and provide your digital ID in order to use search engines like Google. You'll need to provide detailed information about yourself, including biometric data such as facial recognition, which will be stored on tech company servers like those of TikTok in Beijing. We all know how well governments and companies secure your personal details from hackers. Technology editor Alex Zaharov-Reutt from TechAdvice.life warns that it's a slippery slope, with government bureaucratic overreach a guaranteed certainty.
Well, the government and the Prime Minister of Australia has effectively announced that its decision to exempt YouTube from the under-16 social media ban is now being rescinded, and they want to include it in the ban after all from the end of this year. And that, of course, raises all kinds of questions as to how this is going to be enforced. I mean, all of the age verification schemes are more or less not really feasible. How is an AI system going to tell a 15-year-old from one who's 16? And, of course, what's to stop parents from simply logging into their children's devices, whether through the app or through YouTube in the browser, with their username and password? And kids will have unfettered access. And that is before we talk about VPNs and browsers that are known for privacy with VPNs built in or accessing Tor.
The sale of plastic face masks and things like that are likely to rise.
If they're going to use AI facial detection. But if a parent simply logs in to their child's device with their username and
Most kids
password.
know their parents' password anyway.
That's right.
Shouldn't parents be controlling what their kids watch, not the government?
Well, of course. I mean, that's what it comes down to. You know, the parent is the parent, not the government.
Give me a child at the age of 5 and I'll give you the man.
That's exactly right. And really, this all comes down to the government wanting to implement a digital ID system to effectively track every user in Australia.
Well, it does more than that. It lets the government spy on what people are doing, and controlling information is what governments have always been about.
Absolutely, yeah. I mean, the only way to counter misinformation is with good information, with more information, and to let the people make up their own mind. Otherwise, you effectively have what is just a dystopian situation where the government claims to be the sole source of truth. And, you know, it's like Pravda. I mean, you read the approved information or, you know, off to the gulags you go. You know, the New Zealand government Prime Minister at the time, Jacinda Ardern, was saying that, you know, we are the sole single source of truth. Well, no. I mean, that we're no longer a democracy if that's the case. We're a dictatorship. Ronald Reagan has famously stated a few decades ago that liberty is not passed down through the bloodline, but must be fought for and preserved by every generation. And that is the case. The very high reality that this is effectively a backdoor into a digital ID for all citizens. I mean, everything you're doing is going to be spied upon, and already the government
get social
gets
credit points, just like they do in China.
Well,
you're wonderful.
That's right. If you are not adhering to whatever the government policies are, and, you know, you'll have your vaccine passports, you'll have all sorts of things that are inside this digital ID, we're going to a technological dystopia, and that is something that every science fiction movie of note has been warning about for decades.
That's Alex Zaharov-Reutt from Tech Advice. Start Life. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.